Okay, so we're going to talk about the rational root theorem. The rational root theorem states that given this polynomial, so any arbitrary polynomial, all rational roots of the function are of the form p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. So here in this arbitrary polynomial example, p would be all of the factors of, or rather q would be all of the factors of a1, and p, so q equals factors of a1, and then p would be all of the factors of this constant term with no x. Right? So, and notice this states all of the possible rational roots. So for things that are not factorable, what we end up doing is we list all of the possible roots and then we test them out. So for the first example, we're just going to list all the possible rational roots of this quartic function, 2x to the fourth minus 9x cubed minus blah, blah, blah. So I'm just going to start by, so my leading coefficient is 2. That's my leading coefficient. And then my constant term is 10. Right? So then P is going to be all of the factors of 10. And all the factors of 10 could be 1, 2, 5, and 10. But we could have plus or minus on all of these. Similarly, Q is, the leading coefficient is 2. The factors of 2 would just be 1 or 2. So then to list all the possible rational roots, I'm going to divide every number in P by every number in Q. So what that looks like is my possible rational roots, P divided by Q, could just be plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10, and these could all be written as divided by 1. And then we have plus or minus 1/2. Now, plus or minus 2/2 would be 1. We'll write it 2 over 2 plus or minus 5 over 2 plus or minus 10 over 2. And this one is going to equal 1, which we already have. And this one's going to equal 5, which we already have. So normally we wouldn't list out the repeated ones, but it's not the end of the world if you do. So these would be all of the possible rational roots. And then to find out which ones are roots, we'd have to test each one with synthetic division to find out if it is a root. So for that, we made a simpler example. So find all roots of x cubed minus 4x squared plus x plus 6. Now the first thing you should try to do is factor it. Since it has 4 terms, the only option is to try to group it. But if we tried to group it, we would get x times x minus 4 plus 1 times x plus 6, and those things aren't the same, so grouping doesn't work, and we have to resort to some other kind of method. So here our q is just plus or minus 1, so really all of our possible roots are just going to be the factors of p. So p over q, the possible rational roots, will be the factors of 6. So plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So notice this is 2, 4, 6, 8 possible roots. So now we're just going to do synthetic division to test which one is actually a root. So we'll start with checking if 1 is a root. So our coefficients are 1, negative 4, 1, and 6. 1, and that's negative 3. That's negative 3. That's negative 2. That's negative 2. That's 4. So we didn't get a remainder of 0. So no, that's not a root. So because we want remainder of 0. So let's try again. Let's try negative 1. One times negative 1 is negative 1. That makes negative 5. Makes 5. That makes 6. That's negative 6. And that's 0, which is what we want. Yes, we got remainder of 0. So that means that x equals negative 1 is one of our roots. And it left us with a quadratic. This is now x squared minus 5x plus 6. So now, to find the rest of the roots, we can just factor x squared minus 5x plus 6, and that's going to factor to x minus 2 times x minus 3. So our other two roots are x equals 2 and x equals 3. And I'm just going to rewrite the one we already found. So there are our 3 roots for this cubic equation. So we'll do one more example. This one just has, bigger numbers. So this one is a quintic. It's raised to the 5th power. But we'll start with the same procedure. Again, you could try to factor it, but just based on the eye test, the first 3 terms aren't going to group into the same thing as the last 3 terms. So we will not have a way to factor this equation. So since this is 1, I really only need to list the factors of 12. So my P over Q is going to be 1, 2, 3, 4, 6, and 12. So there's no way of knowing before you test which ones are going to work. If you have a nice teacher, then this nice teacher might write problems where if you test the roots in ascending order, like plus or minus 1, plus or minus 2, then one of the first 3 or 4 should work. That's if your teacher is nice. I happen to be nice. I don't like to give you problems where you have to test all the way up to 6 for one to finally work. So, we'll just test 1 first. 1, negative 2, 5, negative 10, 6, negative 12. 1 times 1, that's negative 2 plus 1 is negative 1. That's negative 1, that's 4. 4 times 1 is 4. Negative 10 plus 4 is negative 6, and that makes negative 6. That makes 0. That's 0, and then that's negative 12. So that's a no. We did not get remainder 0. I'm going to erase all of this and start over. And now we will test negative 1. 1 times negative 1 is negative 1. Makes negative 3. And then that makes 3, and that's 8. Negative 8. Negative 18. Positive 18. 24. Negative 24. Negative 36. So that's a no. As you can see, this can get a little bit tedious. But if you're able to do synthetic division, it's not difficult. It's just kind of obnoxious. So, on to positive 2. I hope this one works. 0. 0 times 2 is 0. 5 plus 0 is 5. 5 times 2 is 10. Negative 10 plus 10 is 0. 0 times 2 is 0. 6. 6 times 2, 12. 0. Yay! We got remainder 0. We are happy. And we've now reduced it into x to the fourth plus, so that's 0x cubed, so 5x squared plus 0x plus 6. And conveniently, this one is something that we know how to factor. This is notice the degrees go 4, 2, 0, so this one will work with a quadratic form. So if we change this equation to now be, so we set x squared equal to u, then we have u squared plus 5u plus 6 equals 0, which we can factor into u plus 2 times u plus 3, and then we would get u equals -2, or u equals -3, and then remembering that x squared was equal to u, so this is x squared equals -2. So then x equals plus or minus I square root 2. And over here we get x squared equals -3. So x equals plus or minus I square root 3. So there's our 5 solutions. We have plus or minus I root 2, plus or minus I root 3, and up here we got x equals 2. So notice that there was no way to do this problem without first testing out rational roots because it wasn't factorable at the beginning. So the only way to solve this problem algebraically was this guess and check method. But it's a lot better. So the rational root theorem allows us to narrow down our guess and check instead of just like blindly going 1, 2, 3, 4, 5, 6 until we find something that works. The rational root theorem gives us a finite list. So only in this case we had 2, 3, 4, 5, 6, 12 numbers to choose from. And if none of those worked, then we'd be SOL, and we'd have to, well, it wouldn't be factorable, and it probably wouldn't have any rational roots. But you won't have to worry about problems like this. So if you're doing rational root theorem, and you've tested your whole list, and none of them work,